All right, let's get started. Welcome everybody to this ATA webinar. Myself, Adam Green, and Chris Dostojc from ATA will be talking about HEEDS and the HEEDS Automated Design Space Exploration for Bohning arrow design. Just some housekeeping. Everyone is muted right now, and you can write things into the chat. At the end of the meeting, we'll open all of the mute on the meeting so that you can talk to us and talk to the other members of the panel. So basically, let's kick off. So I'm going to do a very quick intro of ATTA Engineering and HEEDS, and then I'll really pass the ball to Chris for the main event to talk about this work that he put together for the work on the arrow. And so those of you who don't know us, we're ATTA Engineering, our engineering consulting group based primarily in California. We're an employee-owned company, and we're very expert at the things that we do. We tend to do many of the hard projects in the US and globally for engineering consulting. And we have over 180 people, and really over 34 of them are PhDs and beyond. So we're a very skilled group of engineers doing the hardest tasks. And we work in various industries, primarily aerospace and defense, but also some robotics and controls. Themed entertainment is interesting for us too, some of the theme parks, and a few other smaller industries, industry and consumer products. And one of the key things is that we are an employee-owned company. So everyone on the line today, Chris and I, are employee owners, which means that we pretty much take everything personally. But we really strive to make all of our customers very happy. And it's really great to be in a company where everybody feels that way. And really, as part of that, we are committed to excellence, and people recognize that, and especially NASA and some others over the years. We've got many awards. The latest is that the green one in the middle there, the SBA Tibbetts Award. But NASA and NASA JPL over the years have really rewarded us a lot for much of our work. And so some of the things we really do the design analysis and test, really in focusing on all of those areas. Really today we're talking mainly about design and analysis, and you can see the locations where we work are mostly centers of aerospace areas of excellence, and so you can see we have offices in all of these locations across the US. And some people aren't quite familiar with where ATA came from, but we really started in 2000. But before that, we were a testing group within SDRC, the original authors of graphics and ideas. And so ATA has a really strong legacy and connection to both NX, which is what graphics and became, together with a strong connection with Siemens. And over the years, we've grown that to be even stronger, being partners with Siemens, selling and supporting software, growing and opening offices. And then 2018, we extended our relationship to include supporting and selling Star CCM Plus and HEEDS. Hence, it's kind of taken us to where we are today. And so our software services, we are a platinum reseller, which really kind of talks about the amount of business that we do. But we have a lot of facets to the offering that we give to our clients, from support to software implementation to training materials for Nastran, especially really for the whole of Siemens globally, as well as preferred training provider for pretty much all of the tools listed in the center there, from Nastran to STAR to FEMAP. And so forth, including HEEDS when needed. And so that's ATA in a nutshell. And I thought I would then really talk about HEEDS in terms of its application to this project. And really, arrows don't really fall easily into an industry niche. So much of this is from an aerospace and defense presentation that I think is the closest. And so really the real question is what is HEEDS? And really it's a product and a framework for multidisciplinary design analysis and optimization, which is an acronym is MDAO. But really it's a tool that brings together lots of other techniques and analysis packages that really help accelerate their use. And you'll see what I mean in a moment as we talk about that some more. But it really helps people explore design spaces and really do things much faster than really ever done before. And so Siemens obviously has a lot of tools in the sim center space, and HEEDS pretty much works with all of those across simulation, mechanical simulation, and all the way through to physical testing. Really, the whole suite of tools that Siemens creates, HEEDS can talk to and drive. And in addition, much though we hope everyone is using Siemens tools, and in the real world we know that they're using other tools, and so HEEDS also connects to other engineering tools in the marketplace. And so that's really what makes it most powerful, is that it can really talk to any tool that you may have in your analysis toolbox. HEEDS can basically turbocharge or get more out of the same tools. So if you're spending money on tools and you want to get a better ROI, HEEDS can help you get to that point and really get more from those same tools. So there's several advantages, or many advantages, using HEEDS. Obviously, ease of use is a key one, and you'll really see that when Chris takes the stage to show it to us a little more. But it's very simple in terms of how to use it and how to get the best from workflows. Basically, it's helping customers really do things much faster, because you can automate processes, and instead of doing 2 or 3 manual processes, do 100 or 200 to look at the different designs. It integrates really with every CAD and CAE tool out there. Not quite everyone, but we think everyone, and really lets people come up with better solutions that really weren't attainable before. And then other tools within it let you gain deeper insight, much more engineering insight into what's really going on in a product. Really, that comes out of some of the analysis and the visualization that HEEDS can provide. And then lastly, the support team, not only ATA, but also Siemens and the HEEDS team. I know some of them are on board today, so welcome everyone. And really, the whole team makes using HEEDS very effective. And so what actually is it? And really, it's a combination of four key technologies. And the first one is process automation. It's one that ATA has actually embraced for a number of years, and before we started using HEEDS as a niche expertise in-house, moving data around from application codes to another code to really automate processes. And HEEDS makes that so easy for us and for our clients to actually create automated workflows, really just by dragging and dropping icons onto a workflow sheet that can then be configured. It really is that simple. So the process automation piece, even in its own right, is a very powerful tool. Efficient search, the Sherpa algorithm, I'm not going to go into that right now in terms of details, but it really does let you explore design spaces, not only well and accurately, but also with economies of compute and cost issues. And then lastly, well, not lastly, you basically distributed execution. If you want to put things either on your own cloud HP or your own cloud systems or your own HPC systems, then you can certainly do that. And we do that often at ATA, and we're using our own in-house HPCs, but we also have thrown work out to rescale in an automated way as a cloud provider, and AWS too. And then lastly, really the visualization tools that HEEDS provides really lets you dive into the results and the data in a detailed way to really understand the correlations between variables, whatever might be going on inside the design process that you're looking at. You can really dive deeply into the issues that in play and really understand better from an engineering perspective what's going on. And so these are some aerospace case studies, and here's some listed applications. I won't read them out, but you can see that the very diverse areas of applications that HEEDS can be applied to. And the reality is that it can be applied to almost anything where you can drive an automated process. And so those results could be just improve performance, reduce weight and cost, greater safety, things like that, and just really increased innovation. So in the aerospace market, all of those things tend to offer huge value in terms of design improvements. If you can reduce weight, you can reduce costs of both aircraft or satellites, and really just improving your designs can really have large return on investment for software and time in the design space. So here's a few examples of that, and one of the key one that I'm quite familiar with is a United Technologies aircraft thrust reverser, and this is a star CCM Plus model, and you can see down here on the right, here's the loop. It was a parametric CAD model where the geometry was totally parameterized in NX, and then the loop was basically modifying the geometry, looking for better thrust reverser designs. And so a thrust reverser, it seems logical based on its name, but when an aircraft lands, these vents on the side of a motor will open up and push air backwards as best they can to slow the aircraft. And so to do that means you can slow an aircraft more quickly, but also you can create less wear and tear on the device if it's more efficient. So in this case, there was 11 geometric design variables were considered. And if you think about that in terms of how you could manage that either in your head or in the spreadsheet, HEEDS can manage that for you. 11 design variables is a lot when you think of all of those permutations. But HEEDS was able to evaluate 160 designs in just 36 hours running on a parallel system with a simplified 2D model, and really came up with some better designs. And looking at the result there, you can see improved performance by 49%, which was a huge result for basically optimizing the flow in the thrust reverser. So you can see how HEEDS did that. It basically modified the geometry, looked at the resulting star models, and came up with basically the design that was most improved, while fulfilling a lot of other constraints. And so when you look at the baseline, you can see that the numbers there's coefficient of drag, and then the CVX is the thrust, or the reduction in thrust. Then basically the higher the number, the better. And you can see that the best design after running it through this process was significantly better. But not only that, if you see the imagery at the very bottom, it's a little small, but you can see why it's better. You can see why the air turned more. You can see why it's more efficient. And then that in itself helps the engineer understand where to go next, maybe, or even if this design is adequate. And so that's a kind of a fluid example. Another example in this case is with running with Abacus and SpaceX on a satellite model, where it was basically minimize the mass of a rocket engine bracket. And obviously in space flight and space applications, weight is key to reduce costs of launch. And so in this case, it was basically an NX CAD model being driven by into Abacus to look at the strength and the weight. So keeping the strength adequate, but reducing the weight. And so you can see that this would be simpler in some areas than the CFD model, but even in this case, 120 Abacus models were run and resulted in a 9% weight reduction while still maintaining the constraints of strength that it needed. So a 9% weight reduction resulted in a $500,000 cost reduction, which again is very high. And then this example is of a turbo pump from Mechanical Designs, and they use CF Turbo and Star CCM Plus to drive the loop. And you can see on the right there's a chart as HEEDS progresses. It is looking at coming up with basically a more efficient flow to create more power from the same RPM. And so by modifying the vane geometry, the number of vanes, the vane shape, it explores the design space and can give you an answer. And we won't watch all of that because that takes a little while. But if we go to the end, you can see that HEEDS ran, it's about 200 cases, and it settled in a much better design. And again, this is all automatic. This is no man in the loop. This was run for a few days and basically gave better answers. And so this is another one of a basically a stress and strain calculation type model. Again, HEEDS driving FE tool to look at strength versus a margin of safety. And so in this particular one, you can see it was a complete model of the wing versus trying to get it much lighter. And so again, the idea here is that coming up with a design that firstly meets the constraints of the design application, the strength, the lift and so forth, but also while reducing cost wherever it can. And so this last one is one that I'm more familiar with, and it's defense rather than aerospace, but it's actually a marine case of designing a ship for looking at the different geometries in a ship study. So in this case, the CAD was set up in a parametric way, and these are the variables for the CAD: the length, the beam, the shape of the bow, things like that. And that animation, you could see how they varied. And then when it's set up in a HEEDS loop, you can see that basically NX and star CCM plus we use for the geometry creation, which is the box on the left here. Then part of the loop is to calculate the weight of the steel in the ship for that geometry. Then star will do a hydrostatic calculation to figure out the sinkage and where the ship will actually float. And then that data is passed on to a full star CCM plus CFD model for basically looking at the flow around the ship. And so again, you can visualize that this is quite a sophisticated model. That the CFD was quite lengthy, but again, by doing it automatically, it can be left to run continuously and evaluate, excuse me, a lot of designs. And so in that case, you know, that was run on a mixture in IT environment. So he just couldn't have been run on a laptop. The CAD side of things, NX for creating the geometry, could have been run really on another laptop. The hydrostatics on probably a mid-size workstation, and then the actual CFD again on an HPC cluster, either locally or in the cloud. But you can see that 500 designs evaluated. But only four days of wall clock time. That's because HEEDS is able to run things in parallel as well. So it could run some of these concurrently at any time. And so in summary, then really going back to where we started, you know, the four pieces that make up HEEDS and why it's so great: the process automation, the efficient search, distributed execution, insight and discovery. All of these things that we're going to see in Chris's presentation. So with that, I thank you, and I will pass the ball to Chris.
As Adam mentioned, my name is Chris Ostojic. I'm an engineer here at ATTA Engineering, and I'm going to present to you how we used HEEDS and star CCM to help Bohning in an automated design improvement of a crossbow arrow vane. So just a quick review, arrow vanes have significant impact on both stability and accuracy of arrows. The lift and drag experienced by an arrow vane shifts the center of pressure aftward on the arrow, which produces a stabilizing moment on the arrow. And then if you further offset the vane so that it's at an angle with the arrow axis, it creates an axial moment on the arrow that causes the arrow to spin and create spin stabilization. This arrow vane design, and I guess arrow design in general, has traditionally been based on experience and tribal knowledge, which is done very well for thousands of years, I guess. But due to time and cost, R&D is limited to a sparse parametric design space using the traditional design, prototype, test workflow. So what we've done is used HEEDS to perform an automated multidisciplinary optimization to increase arrow vane performance by investigating a broad and full parameter space. So as I've mentioned, we've used HEEDS here to improve the performance of an existing Bohning crossbow vane. The Bohning company is highly regarded as a leading manufacturer of performance archery equipment, and they had a desire to accelerate their design cycle early in the process using a computational approach. So as part of that, we've used HEEDS to orchestrate an automated, intelligent design space exploration using 4 high fidelity CFD simulations in parallel per design iteration and we couple that with an approximate 6 degree of freedom trajectory analysis that we coded up in Python. So in the upper right, I'm just showing the kind of baseline vane design that we started with. And we're placing this on this 20-inch arrow shaft with a vented broadhead shown on the lower portion of the screen. Okay, so in this process that we set up in HEEDS, there's 3 steps. On the left here, HEEDS makes geometry modifications, and then in the middle is kind of where all of the computations take place. And then on the right side of the screen shows kind of where HEEDS assesses the results of the simulation. So going back to the left side of the screen, we first start with our parameterized vane, which HEEDS directs so that we get different shapes and designs of vanes. We've parameterized the vane using 5 variables, which is H or height, L or length, R or leading edge radius, TE or trailing edge concavity, which can either be negative or positive, and vane thickness. So HEEDS will direct the shape of that vane, the values of those parameters, and then that vane is added to that 20-inch shaft that I showed in the previous slide, and given a 1 degree left offset to induce that axial rotation. Moving to the middle is where the computations again take place. You see we have 4 steady CFD simulations set up, and each of these simulations represents the arrow in a different orientation. There's one where the arrow is flying straight, one where the arrow is yawed upwards, or sorry, yawed sideways, one where it's pitched upwards, and one where it's got a rotation imparted on it. Those simulations generate aerodynamic coefficients on this particular design iteration, which then get passed to this Python-based trajectory analysis. So the trajectory analysis takes the mass properties of this particular design iteration, the aerodynamic coefficients, integrates them over time to kind of simulate the flight of the arrow downrange 100 yards to the plane of the target. So one thing I mentioned is not only were the aerodynamic coefficients needed, but also the mass properties of the arrow. So each time we change the vane, it changes the mass of the arrow, the center of gravity, moments of inertia, etc. These could be done in a separate CAD package. As Adam mentioned, there's no problem with putting a CAD package at the beginning of this loop. But the geometry was simple enough that we thought we might as well do this all in Star CCM+. So although Star isn't a full CAD tool, it's able to do all the CAD operations that we needed for this arrow vane design study. Of course, we used the native 3D CAD tool within the Star GUI to do the geometry modifications to the arrow vane, but we also used Star's robust measure and flexible field functions to calculate the mass properties by simply meshing the solid arrow and then assigning it to kind of an inactive computational region, and then using volume integral reports and field functions to numerically integrate the mass, center of gravity, and moments of inertia. So as I've mentioned, the computational portions of this study were done in Star CCM Plus and Python. In Star CCM Plus, we use the coupled solver. This is a crossbow arrow. It flies a bit faster than just a normal bow and arrow, and kind of is in the compressible regime. So we use the coupled solver for that, Mentor SST turbulence model, and a moving reference frame in the case for that rotating arrow. All of these simulations were also steady. For meshing, we use the polyhedral mesher with prism layers on the arrow surface, and we kept the wall Y plus under 5 over the entire aero surface to ensure that we were getting accurate results. And this resulted in about 12 million finite volume cells per design iteration. To accomplish the trajectory analysis, we used a 4-stage Runge-Kutta method to integrate a system of ODEs where we would integrate over time this state vector X, which just contains the arrow pitch, yaw, velocity, location, and rotation rate. The integration is also based on this gust velocity, which is just a lateral wind gust profile shown on the right side of the screen. The arrow was given initial conditions of streamwise velocity, or I guess downstream velocity of 400 feet per second, and a small vertical velocity of 3.75 feet per second. And then again, the result was reported at a virtual kind of target 100 yards downfield. So these computational models are very easy to set up in HEEDS, especially with star CCM and Python, because HEEDS, as Adam mentioned, provides these analysis portals. So for instance, I'll just focus on one of the star CCM plus analyses here. To set this up, you simply drag a star CCM plus analysis portal into the process here, and then start adding input files. So since this analysis portal is set up, HEEDS knows what to expect to manage a star CCM plus simulation. So it asks you, okay, select the input file, and then it recognizes that the input file containing all of the analysis parameters, as well as the file containing the analysis results, they're just the same file. So you pull those files in, and then HEEDS automatically identifies the parameters that you might want to set to run the analysis, and identifies the quantities that might be the response variables that you're interested in. Now it knows to accept or to expect this file, but also has the flexibility to allow you to include other files. So you might notice here below this star CCM plus sim file, I've got this runvert.slurm file, and that's just a slurm submission script that I've included so that I can send these jobs from my local machine to our cluster. And this is the slurm submission script to manage the submission of that through our slurm cluster manager. All of these, as I mentioned, all of these star CCM simulations are run in parallel here. And then only after these simulations complete do the results from those simulations get passed to this Python-based arrow trajectory analysis here. And that's just run locally on my machine. So HEEDS intelligent design space exploration drives our Aero Vane towards an optimal result. It uses its proprietary Sherpa algorithm to intelligently search parameter space and determine a more accurate design. The objectives that we've chosen in this design study are to maximize the roll rate and minimize the distance from the bullseye at 100 yards downrange. And again, the parameters that we've chosen are height, length, thickness, leading edge radius, and trailing edge concavity. And we're varying those each over different ranges, giving them each a resolution of 101. So of course you wouldn't do this, but an exhaustive search of this design space would result in a very large number of simulations. We ran HEEDS for just 32 design iterations, and were able to find a better design knowing that it could query any one of those 10.5 billion simulation points if the design got driven in that direction. And on the right, lower right, I'm just showing 3 design variants to kind of give you an idea of how this vane can change over this parameter space. Okay, so the next step in the process is just to push go, and after that you can go home for the weekend, or depending on how many simulations you're running, go on vacation, whatever. HEEDS really manages the process for you. However, if you do want to check and see how things are progressing, HEEDS keeps you updated on the progress, and you can even do some post-processing while the simulations are running. So it'll just a quick look will give you a range of the parameters that have been looked at so far, as well as the best value, and kind of a histogram showing the distribution of the evaluation or the designs evaluated. It also keeps track of the simulations and skips simulations with errors here. So on the upper left, you're seeing that in this particular study, I had quite a few simulations error out, and this is annoying. It was due to some cluster-related issues causing a bunch of jobs to fail. However, HEEDS is smart enough to know that these things happen, and it shouldn't stop your design space exploration design study. And so it just says, okay, we're skipping that one, moving to the next one, and I can get on with my either work day, or not bother myself during the weekend to rush back and restart anything. And so in this particular case, actually, design optimization history showed a quick improvement in just the first 9 evaluations. The predicted accuracy improved by 30%, and then ran another 23 iterations and eked out another 1%. But you can see kind of how quickly this improved. And just to kind of show you in a more easily understandable way, these are all 32 design iterations are plotted on this target on the upper right of the slide. The initial design is given in this kind of blow up here by the red dot, and the design that was found to be the best design, which was the best weighting between roll rate and accuracy, is shown by the green dot. So not only does HEEDS suggest a best design, but it also provides insight into successful kind of design features for these vanes. Shown here is a plot where distance is plotted on the y-axis, roll rate on the x-axis, and as we've defined what we want, this kind of shows that the designs move from worst to best, going from the upper left to lower right. And you can see that near this kind of best design that I'm showing here that HEEDS has suggested, there are a large number of designs clustered down there. But then there are also other areas that it's looked at to kind of show you examples of what bad designs might look like. For example, this tall blunt design up at the top here, the simulations predict that it has pretty poor accuracy. So if you were if a designer was looking at this, that might give them insight into saying, okay, I definitely want to not design a vane that looks like that. Also, kind of on the other side of the spectrum, this very short, slender design produced an arrow with a very low roll rate, and if that's something that you're interested in, you want to stay away from that as well. HEEDS can, move further in this direction of providing insight by identifying important design parameter correlations through this correlation table, which exposes the relationships between the parameters, the input parameters, and the responses. For example, in this case, we found that the spin rate is very strongly correlated with vane height. It's got a correlation of 0.79 over the population of iterations that we've looked at. So in summary, at the beginning, we wanted to find a more accurate crossbow vane. And the method we employed was HEEDS design space exploration using star CCM plus and coupled with an approximate trajectory analysis. The result was a Aero Vane with a predicted 31% increase in accuracy. And kind of the conclusion of this is that the HEEDS directed star CCM plus and Python design exploration method produced an improved crossbow arrow vane on an HPC cluster with minimal effort from the analyst. And I've got this video here. This is not a result of well, it's not playing very well. So anyway, this video in the upper right is kind of it's not a result of these simulations. It's actually a full transient simulation in star CCM plus of our final vane design. And we've kind of created this video within star CCM plus's screenplay feature, which allows you to direct your video. So it's a nice visualization tool. But going back to this conclusion, kind of going to focus on this last part, minimal effort from the analyst. And this is kind of a hand wavy thing, but I can actually quantify what this word minimal represents. So just in the next slide, earlier in this work, we before we used HEEDS, we kind of assessed manually the performance of 4 arrow variants, and that took about 2 weeks of a single engineering analyst's time. Contrast that, the model setup in HEEDS took about 20 hours of analyst time, and after initial setup, the HEEDS managed the analysis again on 32 arrow variants over the weekend on our cluster. So just I can quickly calculate the speed up by looking at the number of analyst hours and the resulting designs, and found that the ratio is about 64. So HEEDS resulted in a 64 times gain in efficiency. So engineers like me can spend less time submitting jobs that likely have human input errors and monitoring solutions, and more time engineering and letting the machines kind of chunk through the numbers. So that's the end of the material that I have to present. I really appreciate your time and attention, and we can take any questions.
Excellent, thank you, Chris. We appreciate that presentation. And now we will turn off the mute on all of our mics. We can submit questions if anyone has one, either verbally or through the chat in the Zoom system. So if you've got questions, let's have them now. We also have Bob Potter here from Bohning, so that's an exciting thing for us to be able to actually talk to the guys at the end of the line selling these products. So welcome, Bob. Thanks for joining us. And if you've got any questions, let's hear them. Jonathan, can you turn off mute for everyone?
Yeah, so actually the way that'll work is if you want to unmute and ask a question, just shoot me a message and I can give you permission to unmute. But I do have a couple questions from the chat and from the Q&A panel that I can go ahead and read in as well. So these are probably for Adam and Chris, I think. What sort of computing resources are needed for a project like this? And like, what if you don't have those resources available in-house?
So on this particular project, each of these simulations, the trajectory analysis, of course, was just run on my desktop, simple Python script. But each of the star simulations we ran on 16 cores each on our in-house cluster, and ran those in parallel. Each of those took 1 to 2 hours to complete. So that was, I'd say, 128 CPU hours per design iteration. So we're lucky enough to have a very capable cluster on site at ATA. However, we've done similar work with HEEDS, where we've sent jobs from, again, my desktop computer up to the cloud using Rescale computing resources.
Thank you, Chris. Can I add to that too, and
Yeah.
really point out that a lot of the answer to that is also application specific. If you think about the CFD application used here, that's a pretty lengthy simulation compared to doing simpler things. FEA's a little shorter to do structures, and even then there's 1D simulation which is even much faster. So the computer system you might need will often depend on the application that you're using. So if you're using CFD where every point takes hours or even 12 hours on for a huge model, then you need a much bigger system. But if you're running an Excel-based prediction model that might run in seconds, obviously you can use HEEDS and tools on a good laptop to get some good answers. So the spectrum of machine really depends a lot on the application and the application area you're looking at.
Perfect, thank you. Another question that I got in the chat was, Chris, I think you had 2 objectives and 5 parameters. Is there a limit to how many objectives and parameters you can have? And how does HEEDS balance, like if you have multiple design objectives, how does it choose an optimum design from those?
So when you have a single objective, of course, it's much simpler. In the case that we were looking at, we had 2 objectives. So HEEDS then searches the parameter space to kind of develop a Pareto front, and that can be multi-dimensional. In this case, 2-dimensional, but that can exist over multiple dimensions, and it just requires more design iterations to kind of fill that out. Same with the parameter space. One of Adam's examples that he gave, you mentioned that there are 11 parameters. You can go higher than that, but it just requires that more design iterations be evaluated to kind of effectively search that parameter space.
Okay, great. And I think a follow-on question, you have all these different configurations that HEEDS has put together and run. How easy is it to go and look like at an individual run and interrogate those results? Like, do you only get to see what it considers the best, or do you get to see everything along the way?
So yeah, you actually have an option to, well, of course, it keeps track of what it's run and the parameters that it used and the results. If you wanted to go back and kind of run that simulation yourself, there's nothing stopping you from putting those parameters in just the base simulation file and running that again. Alternatively, you do have the option to keep all of the simulation files around that you run, but we've run 32 design iterations times 4, so that's 128 simulations, and each of these is 12 million cells, so it's several gigabytes per simulation file, and so that can kind of jam up your storage a little bit. But you do have that option if you're not worried about storage space.
Okay, perfect. And to everyone who's still hanging around, thank you. Please feel free to continue submitting questions through the chat, through the Q&A tab. You can also request to be unmuted. But I think with that, Adam, I'm going to hand it back over to you to wrap up, I think.
Yeah, I think we're in good shape. Thank you, everyone, for attending. This will be recorded and will be available on demand on the ATA website. So everyone who attended will get a link to see that. And so thanks again for attending. We appreciate it, and we'll wrap up for now. Thanks a lot, everybody. Bye-bye.
Thank you.